That's okay. All right. So here's the story. So if pressure was only pushing down, you would have the weight of Hank just pushing down. You could never lift up a piece of paper. You could never lift up a book. Nothing. But then that leads into the question, fundamentally, what creates air pressure? Okay, because to really understand it, you have to realize, okay, we can talk about it, but what creates pressure? So on an atomic level, imagine this is like an oxygen or a nitrogen molecule. These things are bouncing around, and every time they hit, they change direction. When they change direction, what does that require? A force. Okay? So, and by Newton's third law, for every action there is a reaction. So when it hits and bounces back, that your hand exerts a force on those, and the particle exerts a force on you. Okay? But it's happening billions upon billions of times through these particles that we can't see, right? Because light travels through them unimpeded. So it isn't like the atmosphere has a haze to it, right? Oxygen and nitrogen are cool because basically they let the light travel through them and it doesn't interact with them. Now, so if you look at what happens in terms of pressure, so the other side of this is temperature. So we'll talk about temperature for just a second. So it's been said that a thermometer, which you all have dealt with many times, is like a radar gun for atoms or molecules because it tells you how fast these things are going. So there's three primary scales that you use to measure temperature. You can have Fahrenheit, you can have Celsius, and you can have Kelvin. Okay? So it's been said that Fahrenheit is what human body experiences. Celsius is what water feels. And Kelvin is what atoms feel. Okay? So let me give you an example. So somebody who was really, really bored, had too much time on their hand, realized that the human body is so attuned to differences in temperature that the Fahrenheit scale works very well for humans because we have a good enough detection system that we can detect subtle differences between like 71 degrees Fahrenheit and 72 degrees Fahrenheit. Okay? So Fahrenheit has smaller divisions than Celsius does. So and I can even tell that with you all, like typically the temperature in this room is around 71, 72 degrees. And there's been times when like the air conditioning has not worked and the temperature has just gone up by 2 degrees. It'll go up to like 74. I can completely observe a difference in how you all interact, even with the small change of from 72 degrees to 74 degrees. World of difference. It's like, oh, it's so hot. It's like, it's 2 degrees warmer. That's it. Now, Celsius, and literally this is how they figured out the Celsius scale, is they took a glass tube and filled it up with mercury, and they took that glass tube, put it into a container of freezing water. And when that bottomed out and the water began to freeze, they made a mark where that is on the glass and said, we're going to call that 0. Cool. Then they took that same thermometer and they put it in boiling water. The temperature goes up. It went up to 100. So wherever it started to boil, wherever that mark was when the water boiled, they said, we're going to make this 100. And then they divided that up in between 99 times and then here's the Celsius scale. 0, 100, boom, that's it. Cool. Now, Kelvin is nice because there's two advantages of using the Kelvin scale in terms of this. So pressure and volume, those always have to be positive values. You can't have negative pressure and you can't have negative volume, okay? N is just the number of moles, that's always a positive value. R is your gas law constant, that's always a positive value. So the disadvantage of the Celsius, and the same thing is true of Fahrenheit, is that you can have 0 or negative numbers, which mathematically, if you have a temperature of 0 on there, if you work in the Celsius and the Fahrenheit scale, that becomes a train wreck. Because then, that means either the pressure is zero or the volume is zero. Really doesn't make much sense. Worse yet, if you have a negative temperature, you have like minus 2 Celsius, nice, but then that means either you have negative pressure or you have negative volume, neither one of which make any sense. So that's why we work in the Kelvin scale. So the 0 Kelvin, anybody know what we call 0 Kelvin?
Absolute zero.
Absolute zero. Okay, so that's like a theoretical limit as low as you can get something. So at absolute zero, there's something called entropy, which is like the measure of disorder. So at 0 Kelvin, the amount of entropy of an atom drops to 0. So that's like a theoretical limit. We've got to like 0.001 Kelvin. We've got very, 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 very close to that. But the only way that really happens is if you take a single atom and you put it in a laser trap, and you basically freeze it in place because you lock it in that situation with lasers. Okay, so a lot of times, and you'll see this when you work with ratios, pressure can be in different things, volume can be in different things. But temperature, no matter what, has to be in Kelvin. Now, let's say room temperature right now is about 20 degrees Celsius. Anybody remember how to convert from Celsius into Kelvin?
Add 273.
Add 273, so we're at 293 Kelvin. So if physicists got to vote, we'd measure everything in Kelvin. But that's just going to be a little bit wonky because, oh, what's the temperature? 293. Oh, that's hot. Okay?
That seems so, even though it's not.
So, well, but it's a relative scale. So this is why we don't use Kelvin in normal interactions, because people would be flipping out like, oh, it's so hot, it's 293.
Maybe people would start to think about global warming then.
Well, that's a valid point too. Okay. So, if you look at the units of PV equaling nRT, so in a physics situation, that pressure has to be in newtons per square meter, okay? So the most common conversion you're gonna have is 1 atmosphere is 101,300 newtons per square meter, and that's also known as pascals, okay? On the back of your yellow equation sheet, you have this conversion. They just tell you that 1 atmosphere is like 1.0 times 10 to the 5th newtons per square meter. Use the 101,300 because that's why they got chintzy with that and just called it 1. I don't know. I've never seen that done. So if you do this conversion, which you're going to have to, use the 101,300. Now, here's the cool part of this. In a physics class, because we work off the MKS system, that volume is going to be in cubic meters. Okay, so you can visualize 1 cubic meter is about yay by yay. 1 cubic meter is quite a bit. In chemistry, you use liters. Okay, liter is about like yay. Okay, because in chemistry you tend to deal with smaller volumes. That's why in this lecture in an AP chemistry class, we talk about liter atmospheres. Okay, physics, because we operate off the MKS system, we use newtons per square meter and cubic meters. So here's where the magic happens. If I take newtons per square meter times cubic meters, what do you get?
Newton meters.
You get Newton meters, otherwise known as
Joules.
joules. Okay? So the left side of the equation is going to produce units of joules. Well, the only way this can work is if the right side of the equation produces joules. So, N is your number of moles. So that, on mole conversions, yes, you might have to do some simple mole conversions, okay? Remember, 1 mole is equal to the relative atomic mass measured in what units? Grams, thank you very much. So if you have 1 mole of carbon, that would be how many grams?
12.01.
12.01 grams, because that's the relative atomic mass of carbon. So basically, they took the relative atomic mass, which they already knew, marked out atomic mass units and put grams on the end of it and said, this is what we're going to call a mole. In physics, and we'll get more into this later, we actually work off of something known as kilomoles, which sounds kind of barbaric, but it's just instead of moles, it's kilomoles. So in physics, if you're working in kilomoles, 1 kilomole instead of 12 grams would be 12 kilograms, okay? So it's just a matter of scale, but it's still the same thing. But then Avogadro's number is 6.02 times 10 to the 26th if you're talking kilomoles, so it's order of magnitude higher. Okay, so here's the short version. These are moles. Your N is going to be measuring moles. And your temperature has to be in Kelvin, but we've got to end up in joules. So that's why in a physics class, that R value is 8.314 joules per mole Kelvin. Works out well. The left side of the equation produces units of Newton meters. The right side of the equation produces joules because the moles and the Kelvin cancel out. And miracle of miracles, you get joules, which is Newton meters, so that's why it has to be that way. If you're in a chemistry class, that R is 0.08314 liter atmospheres per mole Kelvin, and that's liter atmospheres because the left side of the equation is, oddly enough, in liter atmospheres, okay? So that's why you have to keep track of, hey, am I using gas laws in a chemistry class, or am I using gas laws in a physics class, because they're not the same thing. Okay, so let's talk about this little gizmo right here.
Yes,
Okay.
we've seen it before.
So I've got a sealed system in here, and there's some pressure because that isn't a vacuum. There's air inside of that. And you have this column of water up here, and you have two kind of pressures involved. You have the pressure inside of here, and then you have the pressure created on the outside by the atmosphere. So this changes, this height changes depending upon the atmospheric pressure. So there's an inverse relationship. So if you remember a couple of weeks ago, we had a pretty bad storm front come through. We had like really strong winds and rain. So if you looked at that, that actually at that point, it was as high as I've ever seen it. It got up to about right here because there's an inverse relationship. So if your outside pressure drops, and your inside pressure is the same, then as that drops, it tries to seek its own equilibrium, so that pressure is higher than the atmospheric pressure, and it goes up. If you're under high pressure, which is kind of what we're under right now, that pushes down, and that level gets pushed up. So here's what I'm going to do. But now we're going to look at this from a different perspective. So I'm going to take my hand, I'm going to wrap it around the world, a little global warming. Okay, as you reference, okay? So I'm going to act like carbon dioxide, and I'm going to trap heat inside of there. So Connor S., I'm going to wrap my hand around the glass globe. What's going to happen to this level outside of here?
I feel like it's gonna rise.
Why?
Because the particles will gain energy from like heat of your hand, and they'll like cause more pressure given the big bulb thing.
So let's talk about this. Okay? I like where you're going with it, but I want to dig a little bit deeper into this whole thing. Okay, so here's this level, and then you got this coming up like this. Okay? And I'm going to put my hand around it. Okay? So my hand is warmer than that surface, okay? That's at about 70 degrees, my hand's at about 97 degrees, okay? So one of the most important things you have to look at is which direction is the energy going to flow. Is it going to flow from my hand to the globe or from the globe back to my hand?
Hands are cool.
Why?
Because your hand is warmer.
So what?
Heat troubles.
More energy. They try to reach equilibrium.
Why?
Don't ask.
Because Mother Nature is
Lazy cream
is lazy prima donna. Mother Nature goes, I'm not going to warm up your hand and have that cool down. It's not, doesn't work. Okay? Mother Nature likes things to be in equilibrium. Okay? So my hand is gonna lose some heat. But what's the mechanism of that heat loss though? So there's this glass barrier in between. So if you think about it, I put my hand around it. Heat, whatever you want to think of that is going to move from my hand, because Mother Nature senses this. So my hand is actually going to get cooler, okay? And then it's going to travel through the glass, and then it's going to hit the particles which you cannot see, okay? Can't see it. And then somehow or another, if Connor S. is right, that's somehow going to interact with that surface and push that level higher. But let's talk about this level out there. There are two things that are trying to keep that level down. What are the two things keeping that level down? What's one of them?
Air pressure.
Yeah. So we have a certain atmospheric pressure, right, which is bombarding that surface. Okay, so air pressure is pushing down it because that's the only direction that it can go. Okay, it can only interact kind of on a downward thing. Chuck, what else is trying to keep it down?
Gravity.
Gravity. So you have two things that are working against it. So gravity and air pressure are trying to keep that column down. So if Connor S. is right, through magic,
I am.
okay, through magic, if you define this as magic, because something's going to happen and we can't see the mechanism, I'm going to wrap my hand around it. Heat is going to travel from the glass to the particles inside. They're going to then gain energy, like there's like a little gas engine on these particles, and we're going to press down on the gas pedal, and they're going to go faster, okay? Now, and Connor S. claims that they are going to strike this surface. Well, do you think I'm going to be able to see like little drops of water or little ripples begin to show up on that surface? No. Okay, it isn't like I see them now. It isn't like I look real close, it's like, oh, I see little stones falling in there. Okay, can't see it. So here's my point. There's a whole bunch of things that are going to appear as magic. Okay, I'm going to wrap my hand around it. This heat is going to travel through the glass, interact with the oxygen and nitrogen molecules, going to interact with the surface, push down more, but we can't even see that happening because it isn't like we can see like the ripples in the water. And then it's going to overcome the force of gravity trying to pull that down and the atmospheric pressure trying to push that down. So let's see if Connor S. is right. So I wrap this around. Connor S., since this is your bat and ball, do you think this is going to happen quickly or is it going to take a while?
I mean, I think pretty quickly.
Okay, like within how much time?
10 seconds. No, 4 seconds.
4 seconds.
Yeah.
What should happen within 4 seconds?
I mean, I think the water level will rise. Shut up, I know what I'm talking about.
Okay, so within 4 seconds, so I'm going to do this, you just do quick, 1,001, 1,002. Okay, when I wrap my hand around it. Okay, you ready?
He did only go to 2.
I know, but I'm just saying, you can go all the way to 4.
Okay.
Okay, are you ready?
C.
Okay, so we're going to watch this level. Okay, ready?
Yeah.
You start counting
Okay.
now.
1, 2, 3, 4.
Okay? So as soon as I wrapped my hand around it, what did it start to do?
Get
Rise.
Yeah, it didn't even take it didn't even take 1,001 for that to happen. But now then you get into, okay, you have these particles. So a lot of times you'll hear me talk, I'll introduce this character of Timmy. Okay? So Timmy is this obnoxious little second grader. Okay? And Timmy likes Skittles. Alright? So if you give Timmy Skittles, he flips out. He goes, I like Skittles! Okay, and he starts running around more. So when I wrap my hand around it, you have this classroom full of Timmys, okay, which they're invisible and you can't see them.
Aww.
But when I wrap my hand around it, I gave the kids Skittles, okay, because I gave them thermal energy. And they're like, I like Skittles, okay? And then they start running around a lot more, and they're going to occupy more space, okay? So when they do that, if you imagine the container being the walls of the classroom, So you have a room full of second graders. Mom comes in and goes, "Hey kids, here's Skittles for everybody." And they all like Skittles. And now they're going to start bouncing off the walls, okay, because they have more energy. But instead of Skittles, actually what happens is photons. So what you just saw in terms of energy transfer was infrared heat. So photons, even though you can't see them because we can't see infrared. So I wrap my hand around it. Photons from my hand were emitted. They traveled through the glass unimpeded. These photons, which you can't see, hit the nitrogen and oxygen molecules, which you can't see. They gained energy, which you can't see. They moved around more. They began to interact with the water, which you can't see. It isn't like you can see that interaction. But then all of a sudden, through magic, the level went up.
What can I say?
Okay? So if you think about it, what seems very simple is actually pretty cool. Because it's like, wow, here's a whole bunch of things happening that I can't see that are making that level go up. Okay? Now, a lot of times when you talk about gas laws, you're comparing like different situations. Like you're going to look at what happens when temperature changes or that type of thing. So if you look at, and this happened to me when it first got cold. So if you look at the tires on your car, like a lot of cars now have like a tire pressure monitoring system. So the very first night when it got really, really cold, I got a low pressure indicator on my truck tires. Why?
It gets colder so that air molecules don't like bounce around.
Okay, there's two words I hate.
Oh, I said it.
You said it. I hate air molecules. There is no such thing as an
The
air
nitrogen and
molecule.
the oxygen
Oh.
knock into each other less and knock into the sides of the tires less.
Okay, so basically, I took Skittles away from the second graders. Okay? Right? I took away the Skittles going, "Oh man, you took away my Skittles." Ah. So they stopped moving around as much. They didn't move around as much. You didn't have as many collisions. The pressure went down. Okay? Cool. Now, shut down that camera. Let's go to the back. We need to do some demo.